like to welcome you to the American Association for the Advancement of Science. We look forward to an excellent and productive discussion amongst all of us today. At the outset, I'd like to thank Dr. Annette Olson, who has worked for the last several months to investigate who might be the right combination of people to discuss these issues, to build this new vision for what this transdisciplinary field of research has achieved and can achieve together in the future. I know Annette's working now to get some slides put on the screen, so I'm sure you've all met her, but she's the one who's responsible for all of the good things that happen today, and we look forward to those. I just have a couple of logistical announcements, and then I'll introduce Dr. Paula Lisowski. Firstly, the Research Competitiveness Program at the American Association for the Advancement of Science has pulled this together as part of our broader program vision to support the capacity development in STEM, whether it's through peer review systems or assessment and impact measurement of large multi-institutional projects and government initiatives, or courses that we develop at a university level to transfer some of that insight that we gain to faculty, researchers, students, and through convening across disciplines the expertise that can advance science. So in that spirit, we've worked through the kind funding of the Sloan Foundation to organize today's event. The event will be live streamed, and that should be happening now, and a warm greeting to everyone who's watching online. Please obviously let us know if there are glitches or issues with that. And it will be recorded, so after the event, the recording of the sessions will be available so that a broader audience, either those who came to the Hill briefing yesterday or those who may participate in future discussions at our National Academies of Science, so that the benefit of our discussions is most widely disseminated. And we will be gathering notes about key points and insights that come from discussions in the panels and the plenary today. So we'll be disseminating to everyone the outcomes as a report and as a point of reference for at least what we consider to be the key issues and key points of collaboration and goals that we share in this sphere. Having said that, I think in the interest of time, I would be glad to introduce Dr. Paula Lisowski from Sloan Foundation, which has now for the second time sponsored a symposium that has this transdisciplinary focus. You may have seen the proceedings of the previous symposium on the microbiome of the built environment, and so this is the second time we've worked together with Sloan to achieve these goals. Dr. Paula Lisowski is a fellow of AAAS, which we're proud of and glad to acknowledge, in the chemistry division. And she's also a pioneering leader in policy and scientific research programs in biosecurity, synthetic biology, microbiology, and chemistry. Her ability to connect talented individuals and emerging science, technologies, and engineering to inspire, accelerate, and produce positive and lasting impact has been constant throughout her career. As program director at the Alfred P. Sloan Foundation, Paula has led innovative and multidisciplinary programs since joining the organization nearly 2 decades ago in 2000. Her accomplishments include the creation and direction of the microbiology of the built environment, MOBE, and chemistry of indoor environments programs at the Sloan Foundation. Prior responsibilities at Sloan include leadership of the biosecurity and synthetic biology programs, which established the foundation for numerous present-day academic, industry, and governmental collaborations. Paula's insight into the ecosystem of philanthropy, early recognition of needs, and ongoing mentoring has enabled grant recipients to make a purposeful and sustainable impact. Dr. Lisowski is a leading expert in biosecurity as well as research oversight, serving as a member of the Executive Committee of the U.S. Environmental Protection Agency's Board of Scientific Counselors. We wish them all of the best. Where she chairs, okay, good. Where she chairs the Homeland Security Research Subcommittee. She is a member of the Council on Foreign Relations, and early in her career, Paula was Vice President of Product Development in the Diagnostics Division at Enzo Biochemical and President of Neotech Corp, a consulting practice bridging the interest of technologies, companies, academia, and governmental agencies. Paula received a Bachelor of Science in Chemistry cum laude from Yale College and a doctorate in biochemistry from MIT. She continues to be involved in the academic and alumni communities at MIT and Yale and has served as a member of the MIT Corporation, president of the MIT Alumni Association, and member of the Yale Alumni Fund Board. Paula was deeply involved with MIT's Initiative for Faculty Race and Diversity Advisory Committee, and she continues to be an advocate for diversity and ongoing supporter of MIT Women in Chemistry. In conclusion, Paul's acumen in board governance, recruitment and development, and donor relations and fundraising has helped many scientific and philanthropic organizations improve their operational efficiency and programmatic outcomes. She's an active board member of the Critical Path Institute, an independent nonprofit organization dedicated to improving the drug development and regulatory process. And in her local community, Paula has been a trustee of the Spondylitis Association of America and board chair of Asphalt Green, a not-for-profit in New York encouraging a lifetime of participation in sports and fitness for individuals of all ages. So it's my honor to introduce Paula to launch our symposium today and to welcome all of you to a fantastic day of discussion. Thank you.
Well, thank you for those very kind words. I need to begin my remarks with a disclaimer. These remarks are my own and do not necessarily reflect the views of my employer, the Alfred P. Sloan Foundation. Good morning, and welcome to the AAAS Symposium on the Chemistry of Indoor Environments. I want to start by thanking the AAAS, but in particular, thanking Annette Olson of the AAAS for her leadership, vision, planning, and attention to detail. It's really quite wonderful, and we will all benefit from that. I also want to thank the speakers and moderators who have traveled internationally to come to this meeting. And I want to thank everyone in the audience, in person and online, for taking the time to participate in this meeting. And I think it's going to be really exciting. So I'm going to give you a little bit of background about the Sloan Foundation and a little bit of background about the indoor chemistry program. So the Alfred P. Sloan Foundation is based in New York City. We're a philanthropic organization that supports research and education in STEM. We provide approximately $80 million a year in grant funding across many, many programs. A very long time ago, the Sloan Foundation gave the money for what became Memorial Sloan Kettering, for what became the Sloan School of Management at MIT. More recently, you may be aware of that we support Sloan Research Fellowships for promising early career faculty in a range of STEM fields. You may have heard of the Sloan Digital Sky Survey. There's a lot of data sharing and instruments there. That's been going on since 2000. Or perhaps you've heard of us while you're watching the American Experience on TV. So at the Sloan Foundation, I direct the Chemistry of Indoor Environments program. And this is support for basic research on the indoor chemistry of the ordinary indoor environments where people live, where they work, where they play. These are not problem buildings. It's just where we are, like what's happening in this room. So why study indoors? Well, to me, it's really interesting because that's where the people are. And there are a variety of references that show that people spend 90% of their time indoors. And I'm sure some other speakers will break that down, but we're inside. We're either at home, at work, in a vehicle. And the indoors is very different from the outdoors. If you look outside, there's bright sun, but the building protects us from that sun. We're not getting sunburns sitting next to the window here. So there's no sunlight to drive chemistry. If you look around, there are lots and lots of surfaces, and the surfaces are made of many different things. We've got carpeting, we've got this beautiful wood paneling, we've got ceiling tiles. We don't have that outdoors, yet those surfaces are available to participate in the indoor chemistry. It's also very comfortable in this room. Right now, it's not too hot, it's not too cold. That's because an HVAC engineer, a long time ago, designed the HVAC system, and then the people who constructed the building and now the people who operate it are providing us with a very pleasant indoor environment. But they really didn't take into account the indoor chemistry. Outdoor air is regulated, and I'm glad it is. I mean, we don't want to have a polluted environment. For whatever reason, indoor air is not. It's not what this is about. But because outdoor air is regulated, there's money to be spent to make sure the scientists can make the measurements so that the air meets the guidelines that have been decided. But we thought it would be important to start looking at indoor air, and we started the program in 2013 by coaxing 4 outstanding atmospheric chemists with their highly sensitive tools and techniques to start exploring indoor chemistry. And some of the people call these people the Core Four. And for brevity, I won't list their collaborators, but Paul Zeman at the University of Colorado at Boulder, Alan Goldstein at Berkeley, who's one of the speakers today, John Abbott at the University of Toronto, and Barb Turpin at the University of North Carolina, who's another speaker today. And when we awarded small grants, we didn't know if they would find interesting science going on indoors. These people were all highly funded, doing excellent work outdoors. Why did they need to come indoors? Well, they can tell you why. So they've been studying sources, the chemical and physical transformation, the role of the people, and the role of the building in indoor chemistry. Today's speakers will be sharing with you some of their very interesting and somewhat surprising findings. Based on the new knowledge generated by this field, I expect that someday we will design, construct, furnish, and operate buildings a little bit differently. So the time has come to review this emerging field and identify future directions and future partners. Today's AAAS symposium on the chemistry of indoor environments will begin that process. Thank you.
Good morning, everyone. My name is Ray Wells, and I'm a research chemist at the National Institute for Occupational Safety and Health, or NIOSH, in Morgantown, West Virginia. And I'm very interested in the indoor environment and the chemistry that occurs there because of the association between, as Paula mentioned earlier, the indoor environment and health effects. And in order to understand that, we have a program at NIOSH called the Health Hazard Evaluation Program, where workers can call in and request assessments of their workplaces to try to find issues or try to understand their work environment. And in the last 5 years, 36% of those HHE requests have dealt with the indoor environment quality. So this is as Paula mentioned, this is an important issue that we're very interested in and trying to understand. So for us, being able to understand or describe the chemical composition of the indoor environment is important for describing the risks to the occupants, explaining the observed health effects, and then also assessing the effectiveness of implemented controls or technologies. We've got 3 very good speakers to start off our day. Rich Corsi, from a dean at Portland State University, but before that he was at UT Austin, where he built a large research group on looking at indoor chemistry and the indoor environment. I'm going to steal a quote from Dustin Poppendick. Rich's passion for indoor quality was shared. He'll share even by passing to a passing squirrel the importance of the indoor environment. That was what I had. Alan Goldstein is a professor at UC Berkeley, and like Paula, he's also a AAAS fellow. His experience in atmospheric chemistry and method development is well known and has been brought in to help us understand the indoor environment in much greater detail. Nina Vance is at the University of Colorado Boulder, and she's been there since 2016, and she'll talk today about some outcomes from the important home chem project. And this is, she'll give you a lot greater detail, but over 60 scientists completely outfitted a home in Texas, the test home, to look at all of the different impacts. And I think Nina's the only person to have 3 Thanksgivings in a month, so that was good. So anyway, I would like to introduce Rich Corsi.
Well, thank you to Ray, and thank you to Dustin, I think, for that quote about squirrels. Thank you to AAAS for organizing and hosting this really important symposium today, and thank you to Paula and the Sloan Foundation, as always, for supporting this important field. So I'm going to prime the pump, I hope, for the rest of the speakers today, and try to do so by answering 7 questions. 7 basic questions about indoor chemistry. Why do we care? What's our motivation? Where does it occur? What are some important sources of reactive pollutants indoors? Why are surfaces important? Are environmental conditions important? Why are building occupants important? And where do we go from here? And so I have to answer those 7 questions in the next 15.5 minutes. And so I ask all of you right now to please fasten your seatbelts. It's going to be a fun ride. So why care? Many of you have seen this before, some of you haven't. This is the secret code for those of us who do indoor air quality research. All of these have the same units, they're years. 79 years is the average life expectancy of an American. The average American will spend 69 of those 79 years, actually slightly more than 69 of those 79 years, domiciled inside buildings. We're indoor creatures. We spend a greater fraction of our lives inside of buildings than whales spend submerged below the surface of the ocean. Think about that. 54 is the total number of years that we will spend inside of our residence, in our home during our lifetime. So our homes are incredibly important environments when it comes to exposure to stuff in air and surfaces. 26 is the total number of years you'll lie horizontally on a mattress with your mouth pushed up against a pillow that's emitting toluene diisocyanate from the polyurethane foam inside. 6 is the total number of years that you'll spend outdoors during your lifetime. 4 is the total number of years you'll spend in a motor vehicle. So by virtue of the fact that we spend so much time indoors, you can imagine that the indoor environment will affect our health, will affect our productivity, will affect our ability to learn. The equation that I've shown here is basically a way of articulating our total mass inhaled of pollution in the indoor environment divided by the total mass of air pollution we inhale in the outdoor environment, all right? So we take the concentration, mass per unit volume indoors, the time spent indoors, the breathing rate indoors, and the same outdoors in the denominator. And then I've just sort of put that in terms of ratios of each of the important terms here. Gone to the literature, found numbers for, we already know how much time we spend indoors, but breathing rates indoors and outdoors, and levels of a wide spectrum of pollutants indoors and outdoors. And what you find when you plug into this very simple equation is that for pollutants of outdoor origin, those that originate outdoors, the ratio of the mass inhaled inside buildings to outdoors is 1 to 10, right? Even for pollutants of outdoor origin, we inhale most of those pollutants indoors. And for pollutants that are primarily of indoor origin, where we see higher levels of those pollutants indoors than outdoors, the ratio ranges from about 25 to 100, depending upon the specific pollutant. So no matter how you cut this, our exposure to air pollution is dominated by air we inhale indoors. You'll hear today that chemistry has a significant influence on pollutants inhaled indoors. And as a building scientist, that excites the heck out of me because that means we have great opportunities to reduce population exposure to air pollution by the way we design and operate our buildings, and perhaps even looking to the future, as Paula just alluded to, perhaps in the future we can actually even optimize chemistry inside of buildings to make the building environment even healthier. So one question down. Number two, where does chemistry occur in buildings? And there's lots of different types of chemistry that happens in buildings. But the answer is everywhere, right? So chemistry happens in the air, in the gas phase, in the occupied space of buildings. It also happens in unoccupied spaces. It happens in attics. It happens in crawl spaces. It happens in wall cavities. It happens in mechanical systems, HVAC systems. It happens on surfaces and inside materials as well. Building materials, furnishings, on us, our hair, our skin, our clothing, and also in unoccupied spaces where materials tend to be a lot different than in the occupied space. It happens in the aqueous phase and in water films that build up on surfaces. It happens in plumbing, premise plumbing. It happens in dishwashers and washing machines. And it happens on airborne particles, in airborne particles, and also those particles that deposit on surfaces. It happens everywhere, right? And some of these really need a lot more exploration. Number three, what are some important reactive sources in the indoor environment? Certainly outdoor environment contributes ozone to the indoor environment. Contributes oxides of nitrogen, unsaturated hydrocarbons. And then in the inside of buildings, we have a lot of primary sources that emit unsaturated VOCs, SVOCs, NOx from combustion sources, lots of unsaturated VOCs from fragrances and air fresheners, and so on and so forth. I list chemistry here because chemistry is also a source of reactive pollutants. Chemistry generates more reactive pollutants, and you're going to hear about that today. But there are lots of sources of reactive pollutants in the indoor environment. In terms of ozone, we know that ozone is continuously coming in from outdoors, day and night, every hour of the day, sometimes more, sometimes less. And so that's the major source of ozone in buildings. But there are also some indoor sources, and I list some of these here, from ion generators to electrostatic precipitators used in mechanical systems, which can be highly effective at removing fine particles from indoor air, but at the same time can generate large amounts of ozone, sometimes a lot more ozone than would come in even from the outdoor environment on a smoggy day, right? The right side here, you see a plot that tries to articulate the importance of even small amounts of ozone generated by an ion generator in the indoor environment. And what you see on this plot is the equivalent outdoor ozone concentration increase, how much we would have to increase outdoor ozone concentrations to give us the same amount of ozone indoors as is generated by an ion generator, emitting, if the green line, 5 milligrams per hour of ozone. And you can see as you change the air exchange rate in a median-sized US home, and you get down to about 0.25 air changes per hour, which is actually not that unrealistic anymore. You're talking about a 40 to 50 part per billion equivalent increase in outdoor ozone concentration. That's a lot, all right? So just putting one small ion generator that emits some ozone in a home can actually contribute a lot of ozone to the indoor environment. So ozone will react with other reactive sources in the indoor environment. So there's been a lot of research done on ozone reactions with terpenes and terpene alcohols that come from green cleaning solutions, fragrances, air fresheners, personal care products. And when ozone reacts with these terpenes and terpene alcohols, you get a whole lot of stuff formed, including low vapor pressure compounds, those little red dots up there. And these low vapor pressure compounds can self-nucleate, they can form particles when they come together, or they can attach to, they can condense on, they can absorb into, they can adsorb to existing particles in the air and grow that particle mass. We call this secondary organic aerosols, SOA, right? So what I've shown in this plot here is a simple example from an experiment we did in a chamber at the University of Texas, about the size of a small residential bathroom, about 11 or 12 cubic meters. And we held the ozone concentration in that chamber. It's somewhere between 30 and 50 ppb. It's been a while now. But, a reasonable ozone concentration. And we looked at what happened when we then placed a solid air freshener inside the chamber. One solid air freshener that emits a mixture of terpenes and terpene alcohols. The vertical axis is the number of particles per cubic centimeter. The horizontal axis is time. And you can see at time equal to 0, between minus 50 and 50, when we put the solid air freshener in the room, we get an increase in the nanoparticles, the 0.02 to 0.1 micron range, from about 6,000 per cubic centimeter up to 700, 800,000 per cubic centimeter, really quickly. That's how fast the chemistry is between ozone and these terpene mixtures. I'm not going to go into the rest of what's on this plot, but you can ask me about it later if you're interested in the growth wave. But if we have this kind of chemistry going on, you're also forming lots of other types of oxidized products that you're going to hear about today. Ozone will also react with stuff from combustion sources, especially nitric oxide. So in this plot, which happened to be an experiment done in a professor's house at the University of Texas. The professor's at the podium right now. And you can see an ozone concentration sort of midday here of around 25 parts per billion in the living room of this house. And right after 1300, right after 3 p.m., 2 gas burners were turned on a stove in the kitchen adjacent to the living room. Watch what happens to the ozone. It's essentially titrated, and it's titrated really quickly when ozone reacts with nitric oxide, which is one of the fastest reactions that happens in air inside homes. The bimolecular reaction rate constant for this reaction is very high. If you assume a steady concentration of 50 parts per billion of nitric oxide, you get essentially a removal rate for ozone or for nitric oxide of 80 per hour. Compare that with a typical air exchange rate in my old home in Austin, which I would measure regularly, about 0.3 to 0.4 per hour. So this is a very fast reaction, very fast removal of ozone. So this is chemistry that happens every day in people's homes, both of the examples that I just showed you. Number 4, why are surfaces important? Well, as Paula alluded to, there's surfaces all around us indoors. The surface area of all the materials in most buildings normalized by the volume of air in the building, the surface to volume ratio, is typically between 300 and 1,000 times what it is outdoors. So pollutants have a lot more surfaces to interact with indoors than they have outdoors, and those pollutant interactions are important. There are dramatic differences between surfaces and materials indoors. The carpet in this room is much different than the skin oils on your face, thank goodness. And these materials are dynamic, they age with time, they accumulate organic matter, particles deposit on them, they change with time, they're emission sources, and there's significant interactions with pollutants. Gases stick to materials, they can stay there for different amounts of times before they desorb. Particles deposit on surfaces, you know that when you clean the dust in your house. Those dust particles or any kind of particles can be transformed by the surfaces and then resuspended, and we breathe those transformed particles. And chemical reactions can also occur. So I'm going to give you some examples of these right now. This one happens to be for, my team did a lot of research on individual chemicals, mixtures of chemicals interacting with lots of different materials. This is just one example of dichlorobenzene, orthodichlorobenzene, reacting with, or sticking to, adsorbing to carpet. And the way to look at the plot on the right is that the vertical axis corresponds to the concentration or the amount of pollutant inside of a stainless steel chamber. What we do is we put these materials in a stainless steel chamber, and we pass high purity air over the materials, and then we start injecting a chemical in, and we look at how much is taken up by the material over time. So the vertical axis is the concentration in the chamber normalized by the concentration that we're injecting into the chamber, and the horizontal axis is time, right? So you can see several curves on here. The important point is that that solid line at the very top is the no-stick line. If there's nothing adsorbing to the material in the chamber, we should be sitting on that no-stick line at the top. The closer we are to that no-stick line, the less adsorption we have. Right here you have the carpet system. So this is the carpet in its full glory with an underlying polyurethane foam cushion, backing, and fibers. And you can see a significant amount of removal. That's pretty far away from the no-stick line for dichlorobenzene to carpet. Right here, the pink squares, you have the nylon fibers. Nylon fibers, almost no dichlorobenzene sticks to the nylon fibers, right? The green triangles are the polypropylene backing that hold the fibers in place, so there's some adsorption to the polypropylene backing. And these dashed blue lines are the bonded urethane cushion, all right, the polyurethane foam underneath the carpet, if it's just sitting there by itself with nothing on top of it, not as a system. The moral of this story is that polyurethane foam is a huge sink for lots of different chemicals in indoor environments. If I was to take a sample of anything in this room to tell you what's been in this room in the past, I would take a sample of polyurethane foam on the seats that you're sitting on right now, all right? Tends to be a reservoir of chemicals that have been in an environment over periods of time. Particles also deposit on surfaces and can be transformed on surfaces. So imagine dust on a bookshelf or on a countertop in your home or on the floor, right? When those dust particles or any kind of particles deposit on a surface, they sit in a small boundary layer, the thickness of the skin of an apple, all right, on that surface. And that boundary layer can be quite concentrated in terms of the level of pollutants that are coming out of the material. Say a plasticizer, phthalates, or flame retardants that are leaching out of the material very slowly, right? So now we're immersing these particles in this boundary layer of relatively high concentration of these chemicals, and the particles can become contaminated, especially the organic portion of the particles. If we then resuspend those particles when we walk on it or our infant crawls on the floor, right, or wherever it is, right, those particles that are contaminated can become a vehicle for the transport of flame retardants and plasticizers and other things into our lungs. So one of my colleagues at the University of Texas did some research in our test house at the University of Texas, a 3-bedroom, 2-bath test house. And what she noticed was that the flooring had lots of butyl-benzyl phthalate in it, a plasticizer. None of the other materials in the house had butyl-benzyl phthalate on it. So she hypothesized that if she collected dust samples from the dust samples in the flooring should have lots of butyl-benzyl phthalate in it, and from other surfaces you'd see less of it. And here's the result, all right? Butyl-benzyl phthalate concentration in micrograms per gram. We're up in the milligram per gram level here for dust samples collected off the floor, which is the red bars, and then off of all the other surfaces, you see the green bars, very little butyl-benzyl phthalate in it. So the surfaces, the materials that particles actually land on can transform the particles, and that affects what we're actually exposed to when those particles become resuspended. We also know that pollutants chemically react with materials. So ozone is the one we know the most about. There's been a lot of research on ozone. Ozone will react with reaction sites on materials, and sometimes those reactions lead to the production of what are called ozone reaction products, or reaction products, which can be released from the material, sometimes almost instantaneously, and sometimes hours to days later, released from the material. And the plot that I show here is a plot that shows deposition velocity. Don't worry about what that means. It's just a measure of sort of how reactive a material is, all right? In this particular case, the fluid mechanics are the same for every material, so the differences that you see are actually due to reactivity. These are for about 10 different green building materials from some research we did about 10 years ago. And the important points here is that if you look at how that reactivity changes with time of exposure to ozone, you see a significant difference in the reactivities between materials. Not all materials are created equal, like has already been said. You see declining reactivity in every single case. As the reaction sites are wiped out on a material, it becomes less active for removing ozone. You see, interestingly, for some of these materials, a non-zero floor. It basically converges to a steady removal rate of ozone. We have reasons why we think that might be happening, but we're not sure. The question is why. And then also when we turn the ozone off and then turn it back on 24 hours, many of these materials regenerate. They go back to their original reactivity, even though they're sealed off in a chamber with no airflow over them. Why, right? So these are questions, we've kind of scratched the surface on many things in the past in this field, and we haven't had the resources to dig deeper and answer some of these questions. And I think this is a really good example of that. I think with more resources and more people coming into this field that have heavy weapons in terms of instrumentation, maybe we'll start to answer some of these questions. Are environmental conditions important? The answer is yes. We typically measure temperature in the air and relative humidity in the air. That's not everything we should be measuring. We should be measuring things like surface temperature indoors and some metrics for mixing conditions in the indoor environment. I show a couple of plots here just for temperature effects. The top plot shows reaction rate constants for ozone and alpha pinene, normalized by the reaction rate constant at 25 degrees C. And what you can see here is you vary over temperatures. You don't see a very big effect especially within the temperature range of buildings, you don't see a big effect on reaction rates in the air. So temperature in buildings doesn't really affect reaction rates in the air. It can have a big effect on secondary organic aerosol formation. So the equilibrium state tends to stay towards the solid phase or the particle phase when you lower temperatures. So even within reasonable temperatures, say 17 to 27 degrees Celsius in an indoor environment, you do get a factor of 3 or so change in secondary organic aerosol formation as you move to cooler temperatures. So in that particular case, temperature of the air does make a difference. And environmental conditions also matter on surfaces. In the left plot here, I show the temperature of the surface of a plastic laminated table put next to a table, and the table is placed next to windows of different efficiency, all right? So we're just going to look at one of those, and that's the least energy efficient, which is the black curve. And what you can see on this black curve as you progress through a day, the temperature of the surface of this table goes from about 24 degrees Celsius to above 34 degrees Celsius. over a 10 degrees Celsius change in the temperature of the surface over the course of the day. Why is that important? Well, that's particularly important if we're emitting semi-vol organic compounds, if we're emitting plasticizers from that surface. A 10 degrees Celsius change in the temperature of many indoor materials that have plasticizers in it can be an order of magnitude increase in emissions, a factor of 10 increase in emissions. So surface temperatures are important, especially when it comes to things like semi-VOC emissions from flame retardants and plasticizers. On the right, okay, Ray? Good, okay, on the right, is a result from some field experiments that we did in homes in Austin, Texas. Wanted to show you the effects of relative humidity or changes in relative humidity on organic compounds in air. We'd go into homes, we'd turn on a humidifier. I know Barbara's going to talk about water-soluble organic compounds in a little bit. We turn on a humidifier, we increase the humidity in reasonable bounds, 40 to 60%, 45 to 65%. We measure the total amount of organic matter in the air before humidifying and after humidifying. Before humidifying is the blue bars, after humidifying is the red bars in this plot. This is abundance per volume of total stuff in the air. We also did mass spec analysis to identify what the red bar was made of, all right? And what we found in the red bars was not chemicals that would be associated with materials in the indoor space, but chemicals that would be associated with having adsorbed to materials. These are fragrances. These are terpenes and terpene alcohols, paradichlorobenzene used in moth repellents, those kinds of things, right? So this is fascinating to me. What does this mean about damp buildings and damp spaces? If things get damp, do we get gushes of chemicals emitted into the air in buildings? If we change our thermostat setting to conserve energy, do we have periods of higher relative humidity indoors? Does that expose us to more chemicals? An area of research need, big research need here, understanding the mechanisms and understanding how we might optimize these effects to purge buildings from things that are stuck to surfaces. Why are building occupants important? Our activities, right? We bring sources into the indoor environment. We plug in air fresheners. We change thermostats. We cook. We modify surfaces by vacuuming and dusting. We influence ventilation by opening windows and so on and forth. But we're also reactive ourselves. Our skin lipids, things like squalene and skin lipids, it's highly unsaturated, is reactive with ozone. Our clothing, personal hygiene products, et cetera. And the plot on the right just shows an experiment from Denmark, from Charlie Wester and Armin Visthaler, that showed two large Danish men, quote, large Danish men, walking into a chamber that was held at 33 parts per billion ozone. At 10 a.m. they walk in, you see a drop in ozone concentration. At the same time, you see a burst and increase in 6-MHO and 4-oxopentanal, which are reaction products with squalene. All right. So where do we go from here? I think I'm out of time, is that right? I am out of time. So I'll just let you look at this. I just want to point out the first one. There's been a lot published on this subject where we've scratched the surface and found some interesting things. I hope those of you that are just getting in the field read the literature. There's a lot of publications, especially on ozone chemistry indoors. Please read the literature, and you'll have access to that slide, I think. Let's have a great day. These are some of my past research sponsors on the lower right. Follow me on Twitter, please. Especially since that's videotaped live here. Follow me on Twitter, everybody. And you can also email me if you have any questions.
Okay. Hi, everybody. I'm Alan Goldstein from the University of California, Berkeley. It's really a pleasure to be here today. Thank you to Paula and the Sloan Foundation for funding all the research I'm going to tell you about. Thanks to AAAS for having us here. And thanks to the people in this picture for doing all the work I'm going to show. It's really their work. This is a bunch of my graduate students and postdocs, plus a very close colleague, Bill Nazarov, who's been a leader in the field of indoor air for his whole career, who recently retired, actually. So I'm going to be talking about bringing atmospheric chemistry home. Now, there's been a lot of work in atmospheric organic chemistry, and I've been spending my career at the heart of that work. I wrote what's really a review paper with Marianne Glacias a couple of years ago, and I want to point out a couple things from that perspective on outdoor air. First of all, we say in the outdoors that the Earth's atmosphere has a huge array of organic compounds. They differ by orders of magnitude in terms of their properties such as size, volatility, reactivity, and the chemistry that they go through, and their impact on climate and health. And so this picture just shows kind of how we think of the outdoors. There's lots of different sources of VOCs. volatile organic compounds. Some of those are natural, some are anthropogenic. They react by being oxidized in the atmosphere, forming a lot of semi-volatile organic compounds, which means they tend to be lower volatility. Some of those can stick to particles or surfaces, and we form these secondary organics that are really important for health, for visibility, for climate. And so in trying to explore this chemistry, the analytical toolbox that we've developed has grown dramatically. There's been really a revolution in mass spectrometry and in the tools that we use to get atmospheric chemicals collected into mass spectrometers over the last decade or so. It's just changed our view completely of outdoor atmospheric chemistry. But I spent the past 3 decades studying this, largely justified by human health concerns. And the fact is that we spend 90% of our time indoors, and 70% of that time is in a residence. And so with Paula's instigation of the Chemistry of the Indoor Environment program, I got pulled in to start looking indoors. And so I say that we've been bringing atmospheric chemistry home, applying this analytical toolbox to understand the environment where we spend most of our time. So indoor air does not equal outdoor air. Buildings are leaky. Sometimes we open windows and doors and we deliberately exchange the air, but even when we're not doing that, there is air exchange through the cracks in the building. Outdoor air impurities can be altered when the air is brought indoors, and indoor emission sources can strongly influence indoor composition. And I can tell you right now, the largest source of organic chemicals in this room right now is all of you. What's the state of knowledge? We just heard a lot about this from Rich, but I want to point out just a few features. One, we know a lot of things are elevated indoors. Two, those sources include building materials, furnishing, occupants, and their activities. But we've really got limited knowledge about source rates, chemistry, and dynamic behavior, and that's largely because the tools that we've had in the past to apply to studying indoor chemistry. So the strategy that we've taken in my group at Berkeley is observe, don't perturb, do detailed investigations at a few sites in normal use, do really high resolution measurements in terms of time, space, and chemical species, and then try to understand the processes that are going on at a very fundamental level so that we can model them in the future, working with the Mochi team that you'll hear from later, or Moki, sorry, Manabu. And we want to investigate the processes, especially for the emissions, the chemistry, and the exposure. So I'm going to show you a little bit of data and tell you, bring you through a story of what we did in one of our very first outings as part of this program. We did residential sampling campaigns in California in normally occupied wood frame single-family homes with no indoor air quality problems that were known. We looked at houses that were built in the 1930s and 40s, which are typical California residences. H1, we looked in the summer and the winter, and H2, we just did the winter measurements. And we measured everything we could. So this is just an example. We put wireless sensors all over the house. We could see where all the occupants were and what they were doing. We had motion sensors. We had sensors on all the appliances, windows and doors, to see if they were open or closed. We had temperature and humidity sensors everywhere. We had the occupants write down everything they did. We measured particles. We did biological sampling. We got at air exchange rates. And we measured lots of trace gases, but I'm not going to talk about any of that. What I'm going to talk about is my favorite subject, the organics. So we're going to talk about volatile organic compounds and semi-volatile organic compounds. Rich introduced both a little bit. I won't go into the instrumentation that we're using for VOCs too much, except to say that we can measure hundreds of species in real time with concentration detection limits down to around a part per trillion, and time response of seconds, okay? So let me show you first some VOC data. And I'm gonna point out that we set up a single instrument with sampling lines to 6 different places, and we switched every 5 minutes between those places. One was outdoors here in red, then in the crawl space, which is below the house, the basement, which is at the bottom of the house, the kitchen and the bedroom areas, and then also in the attic, which is the space above the house. And we did a summer campaign and a winter campaign. Most of the time, the space was occupied, and sometimes it was vacant here in yellow. We just plotting here the sum of all the VOCs that we measured, and note this is a log scale. And a few things should pop out immediately, and I was shocked when I first saw this data, and I hope some of you are too. The first thing to notice is that the outdoor concentrations of the sum of all the VOCs were always an order of magnitude lower than the spaces where we spend our time indoors, in the kitchen and the bedroom. The air in this house is flowing generally. We know this from our tracer release studies. The air is flowing up from the bottom to the top. It goes into vents that are in the crawl space and goes up into the house, into the living spaces, and then out the windows and up through the attic. And so one of the things that's really interesting is that crawl space in the basement, the concentrations are very similar to the outdoors, but the bedroom and the kitchen are really high, and so is the attic. That tells us something really important, that the sources of those VOCs that are indoors have to be coming from indoors. There's no way they can be coming from outdoors, first of all. Second thing I want you to notice about this is that when the house is vacant and when the house is occupied, you see one major difference, and that is no spikes. The average concentration, the lowest concentrations we see indoors, hasn't changed much when you're not doing anything inside the house, when the people aren't there. But the activities that the people were doing when they were in the house were causing these spikes. That tells us that this high background is coming from the stuff in the house, and on top of that, people were doing things, cooking, cleaning, etc., that's adding these spikes. So that tells us the continuous emissions from the indoors are really large, and that occupant activities occasionally cause spikes. Another thing you'll see here is that the winter and summer data don't look all that different. So now let's go a little more specific into the chemicals that are there. This is just comparing the average concentration in the summer versus the winter for chemicals that were in the kitchen. They're colored by their mass to charge ratio, so going from small molecules to big molecules, basically. So think of that as molecular weight. My very favorite molecule is the top one, ethanol. And it turns out that ethanol concentrations inside the home, summer or winter, averaged 100 parts per billion, which is shocking. It's really high. Outdoors, in an urban area like Los Angeles, you can expect to see 3 to 5 ppb of ethanol. Okay, so that's really high. Acetic acid, methanol, all of these relatively light, oxygenated, volatile organic compounds are very high in the house. There's a lot of other chemicals there. One other thing I want to point out, though, is that the winter and summer are mostly the same. Two things stick out in the winter that were higher. One of them is called D5. First, how many of you are wearing antiperspirant? Come on, be honest. A lot of you. Okay. That D5 is cyclic methylsiloxane. It's the dominant ingredient in your antiperspirant, most likely. And it's probably also the dominant volatile organic compound in this room, which means that the dominant VOC in this room right now is coming from your neighbor's armpits, and you're sharing it with them, okay? And it turns out that one of the occupants in the winter got a new product that had D5 in it. It's a common product, it's a common chemical in personal care products, and they put it on, and that elevated concentration is from some of those spikes. Monoterpenes, Rich talked a lot about monoterpenes. When we think in outdoor chemistry about monoterpenes, we think those are some of the dominant chemicals emitted to the atmosphere. They're dominantly emitted by forests, and they react in the atmosphere and are the major source of secondary organic aerosol in much of the US, particularly the southeast US. A typical outdoor concentration in a forest of monoterpenes is less than 1 part per billion. The average in the summer was a little over 1 part per billion in the kitchen and 10 parts per billion in the winter. Why? Where do these monoterpenes come from? First, that's that beautiful lemon smell, or citrus smell that you have in a lot of cleaning products, but also it's coming from citrus itself. And so the occupants in this house only eat fruit when it's in season. Oranges are ripe in the winter. They're eating a bunch of oranges, and that's from eating oranges, that you get 10 ppb of monoterpenes in the house. Okay, so moving on, we invited a bunch of people over for a party, and I show this slide to demonstrate what we can learn with really high high time and response data. So we had all these sensors going. You can see that people woke up in the morning. This is one day. They woke up in the morning. The motion sensor saw them come into the kitchen. They turned on the coffee maker and the toaster. Pyridine is a chemical that's really ugly. It's a benzene ring with a nitrogen in it. And you'd look at that chemical, if you think about health effects, you say, that can't be good for you. It turns out it comes from your coffee. And so it's part of the aroma of the coffee. The ethanol spiked also at that moment. What were they doing? Was that Irish coffee? No. It turns out that they made toast, and bread is a fermented product, and it has a bunch of ethanol in it, and so when you heat it up, the ethanol comes out. And so we see that spike, right? We go a little bit later in the day, and they start cleaning, and we see solvents starting to come out. We see ethanol and acetone. A bit later, they start cooking, and they made ratatouille, so a bunch of vegetables sauteed in oil, and you see lots of sulfur-containing compounds. This ethane thiol plus DMS from the cooking. So then, it's about time for people to show up for the party, right? What happens? Several things. First, everybody got clean and dressed up and reapplied all their personal care products, and the D5 spiked as soon as everybody walked in, right? Then they heated up the food, the ethane thiol, DMS comes out, and they start opening the beer and the wine. And the ethanol went up to 4,300 parts per billion in the house. 4.3 parts per million. That's huge, right? That's really a lot. People left, they started cleaning up, and there's another big spike of ethanol. I don't know if they started drinking again. But I think what they did is they took all the half-empties and they threw them in the sink, and you see this big burst of ethanol come out, right? And at the same time, they started washing the dishes, cleaning up, and you see chloramine coming out. So chloramine is coming from the treated water that's coming in through the tap. And then just a little later, they turn on the dishwasher, and lots more chloramine comes out. And so what you can see here is that with high resolution chemical measurements, high temporal resolution, we can actually look at what's emitted from all these different kinds of events that happen indoors. And we're integrating this and looking at the full chemistry and working on papers that actually say what chemicals come from what kind of activities, how much, and then trying to understand how that matters. So one point I want to make, oh, you're kidding me. Wow, that can't be right. So, no, really, I don't think I could have possibly talked for 14 minutes, but anyway. So we have, when we look at the spiky pattern, what you see is that the spikes in all the VOCs that we measure follows the exact pattern of burner uses in the house. So in other words, most of the spikes that we saw in the data were coming from cooking. And you can see there's a spike at breakfast, lunch, and dinner that is persistent. And if we add up the continuous emissions of all the things that weren't spiky, the things that were at least 10 times as high indoors as outdoors, we see actually that we get a total emission that, I won't go into the numbers too much, but I'll just say that the total emission doubled over a 7-degree temperature range. And so this is the background emission in the house. And that background emission is actually really high. And one of the things you'll hear later from Matt Coggin and maybe some others is maybe all these emissions matter when they get outside. Okay, so Ray, did I really use up my time? I don't think so. I don't think it's possible. Okay, just go. Okay, sorry. Wow, I'm just too excited, I guess. So let's say a few words about semi-volatile organic compounds. I won't get deep into the methods of how we measure these, but the instrumentation that we developed to measure these, we actually invented in my lab. And the questions are, what are the SVOCs in the home? how do building characteristics affect the source's chemistry and dynamics, and then how does occupancy and activity affect concentrations. And semi-volatile compounds are sticking to all the surfaces. They're coming off the people, off the furniture, from cooking, from outdoors, and we want to understand their dynamics. When we look at a chromatogram of the semi-volatiles indoors, what we're seeing is the stuff that comes out early in the GC retention time is the lighter stuff, and the heavier stuff, the more sticky stuff comes out later. This is a really crazy chromatogram. For any of you who do this kind of analytical chemistry, you realize that that's a really, really full chromatogram, lots of different chemicals in there. We can pick out individual ones, and here are the phthalates, for example, and some other compounds that Rich talked about. And we can see that there's lots and lots of different chemicals with different functionalities here. I'm going to just go into detail on a few. But first, I want to say that this is what the outdoor SVOC chromatogram looks like. And when you go indoors, it looks like that. The phthalates that Rich was talking about are like a needle in a haystack. They're just one of many, many, many thousands of chemicals, actually, that are there. So when this is happening indoors, you think, oh my God, I should clean this place, right? What happens when you clean? It turns out that you actually increase the concentration of a lot of these things. Why? Because you're putting a solvent on these surfaces that are covered in organics, and you're changing the pH, and you're liberating a lot of them into the gas phase. Wow. Let's just cook dinner and relax about all this, right? So what happens when we cook dinner? It looks like that. And you get way more chemicals, and we're getting to heavier chemicals. Stearic acid comes from cooking with oil. Cholesterol comes from cooking meat. And a lot of these are in the particle phase. When we look at the total SVOCs as a function of time, we note a couple of things. One, there's a wiggly pattern here, and I can just tell you that that follows temperature. That's because the heating system is going on and off to maintain the temperature of the house. The vacant period and the occupied period look pretty similar, but there's extra spikes in the occupied period. Most of those spikes have to do with cooking. You can see the cholesterol and stearic acid coming from the cooking, and that's mostly in the particle phase. And so those get flushed out of the house really quickly when they're in the particle phase. But then when we clean, we see some nonanol and terpineol, and those go away much more slowly. This is why when your house gets cleaned, you come back a day later and it still smells clean, right? So you can all realize that that's going on, but the gas phase compounds leave much more slowly than the particle phase compounds. Just a couple more slides. I'm amazed if I did that. Okay, yeah, okay, sorry. Indoor SVOC concentration is driven by temperature. And if you look at the integral of all the SVOCs, what we see is that it really follows temperature. And the only time that total SVOC doesn't follow temperature is when we have cooking, cleaning events, or candles. And so there's a background level of SVOCs that's driven by uptake and release that's temperature-driven equilibrium with surfaces. So one thing that we might want to do is we might want to vent the house and flush all those VOCs outside, right? So we did an experiment where we vented the house, and this is the total SVOCs indoors, and this is outdoors. You can see that indoors is 5 times as high, and when we vent, we can get it down to the outdoor levels, but as soon as we close all those doors and windows, within about 5 hours, we're back to where we were, because there's a huge reservoir of organics on all the surfaces. Okay, so bringing atmospheric chemistry home, I'll just put this up as a little summary to say that we've been applying all these new analytical tools, and we're learning a lot. And one of the things that we're learning, one of the main things we're learning is that occupant activities do contribute to the VOCs and SVOCs indoors, but most of what's there is there whether the people are there or not. There's a huge emission of VOCs and SVOCs that is temperature-driven. There's a lot of chemistry involved, and the volatility of those compounds is really key to their behavior. I'll stop there.
Hi everyone, my name is Marina Vance. I go by Nina. I'm at the University of Colorado in Boulder. And today I'm here to talk to you about the need for collaborative field studies in indoor chemistry and indoor air quality in general. By collaboration, we can reach a lot more. We can probe a lot deeper into the science, and we hopefully will have more findings to share with the scientific community. So I have one example of a large collaborative field study that we led last year called HomeChem. So before I talk about HomeChem, I'd like to bring up a little bit of history. There have been previous collaborative indoor air field campaigns, some very large ones. We are not the first ones. We are standing in the shoulders of giants here. So there are 3 studies that I'd like to highlight. The first one is the TEAM study funded by EPA. They followed 650 people in 4 states, and they looked at their personal exposures to about 20 VOCs. And it happened in the late 70s, early 80s. And then about 15 years after that, the RIOPA study investigated 100 US homes in 3 states, and they looked at indoor-outdoor relationships of volatile organic compounds and PM2.5. And then about 10 years after that, there's a study in Europe called Office Air. They investigated 37 office buildings in 8 European countries. And again, they were looking at these indoor-outdoor relationships of VOCs, particulate matter composition, and more. So there's something that is in common if you think about these big studies, right? They try to look at many buildings, as many as they could, and they were looking at a few particular species, chemical species of interest or indoor pollutants of interest, because obviously you can't look at everything everywhere all the time, right? So you have to make a choice. And their choice was to look at as many buildings as possible to try to be as representative as they could of cities or countries or states. So their focus was on indoor sources of air pollutants, but also the penetration of outdoor air pollutants. The study that I'm going to talk to you about today is sort of the flip opposite of that. So our study used one house, so we try to keep that one house constant, and we try to investigate as many chemical species as we possibly could. We try to measure everything that we could. Our focus was, again, still on indoor sources, penetration of outdoor air pollutants, but beyond that, we try to probe deeper into the fundamental chemical and reactions, the physical mechanisms, the transformations that are going on indoors, and hopefully that level of fundamental science can be translated to other homes as well. So this is our study. It's called HomeChem. It stands for House Observations of Microbial and Environmental Chemistry. The study took place in Austin, Texas last summer, so around May, June of 2018. We had a pretty detailed investigation in indoor chemistry, as detailed as we could possibly make it at the time. With over 30 state-of-the-art instruments. We had over 20 faculty members from 13 universities in the US and in Canada. We also had some industrial and governmental partners joining the study, loaning us instrumentation and their expertise. So we ended up with over 60 researchers on site. At this point, I'd like to acknowledge my co-principal investigator. She's Professor Delphine Farmer from Colorado State University in the Department of Chemistry. And you can see at the bottom there the logo of all the institutions that were collaborating with us on site. So as I mentioned, the different thing that we did from previous collaborative studies is that we chose one home. So we picked very carefully what home we were going to use, and the home we chose was the UT Austin Test House, or the U Test House. This house was operated by Professor Attila Novoselak at UT Austin. I'd like to acknowledge his hard work during this campaign. And this house is a research instrument. So nobody lives in this house. It wasn't built for a living. It was built as a research instrument. And UT Austin has had that house for over 10 years. It was actually purchased through an IGERT fund that Dr. Corsi led over 10 years ago. And since then, the house has been intensely characterized and used for building efficiency and indoor quality studies. So for us, it felt like a really good place to have our study, since the home had already been characterized so well. So the home has several HVAC systems that we could choose from, continuous outdoor air supply, and also monitoring of temperatures on surfaces and in different rooms. Energy consumption was also very, very well monitored, so it was a very good candidate for a study. So now I'd like to present to you a little bit of the instrumentation and the level of collaboration we had in the study by using this wonderful photo from our open house day. Not everybody's in the photo, of course, but everybody that was there that day is in the photo. And I'm not going to get into details of the instruments, but I'll show you sort of the breadth of the analyses. So we had several teams measuring aerosol physics, so size distributions, concentrations of particles, and their dynamics over time, ranging from 1 nanometer to 20 microns, different locations around the house. And you can see the logos of the institutions that were collaborating on bringing their instrumentation. When it comes to aerosol chemistry, so the composition of particles, we also had a variety of aerosol mass spectrometers in the study, including the Goldstein group, with the same instrumentation that Alan just presented before. We also had measurements, of course, of volatile organic compounds with a variety of mass spectrometers from different institutions. And finally, we also had measurements of oxidants and other trace gas compounds. And finally, measurements on surfaces in the microbiome. So these teams were actually the only offline teams in the campaign. They came over and they took swabs of all of the surfaces, brought them back to their labs to evaluate both the chemistry and try to understand the microbiome of the house. So that gives you a little bit of flavor for home chem in terms of instrumentation. But I'd like to talk a little bit about the experimental design as well. So I mentioned this is a field study. Usually in a field study, you go out into the world and you try to see the reality of what's going on without interfering much. But in our case, we had a little bit of both. So we couldn't really dictate outdoor pollution and how much is coming into the house. We can't really control the home. It's not a glass, a box. So we couldn't control those things, but we could control the types of activities that we performed. So we had a very clear activity schedule, and we were trying to take as many notes as possible on what was being performed at any given time. And we chose 3 categories of perturbation that are hopefully activities you all perform in your home on a daily basis. So we try to focus on cooking, cleaning, and occupation and the use of personal care products. As Alan mentioned before, that's also, human occupancy plays a big role in indoor chemistry, so we wanted to probe into that as well. We had 2 different types of experiments. The first, we call them sequential, so basically we're repeating the same activity over and over, trying to get as many replicates as we could. And another kind that to me was a little bit more interesting, we call them layered activities. So a more realistic representation of our home. Volunteers would come in, cook breakfast, and they would clean a little bit, and then cook lunch, clean a little bit, and then cook dinner. So maybe this is a much cleaner home than an average home who cleans their house twice a day. But at the end of the day, we were trying to watch for that interplay of emissions throughout the day in a more realistic fashion. So in the end of the day, we wonder if this is really a field study that's really well controlled, or if we have a more realistic chamber study. We're sort of in between that. So basically, we had a very busy day. What you see here is our experimental schedule. We're swimming in data right now. The experiment only happened a year ago, and a lot of these measurement techniques take a long time to calibrate and go through the data. So we're still working on that. But today, I'll show you a little bit of data from one of the 4 stir fries we cooked on June 17. So what you see here is a time series. So on the x-axis is time. On the y-axis is number concentration of particles. Number, not number. So what you see here is the concentration of particles of all sizes, ranging from 0.1 microns to 20 microns in size. And you can't really see much beyond the pink line, and that's because all the lines are collapsed. That means that on a number basis, all the particles we observed indoors, over 99% of the particles, are below 100 nanometers in size. These particles are very important from a health perspective, of course. We understand they can travel deeper into the respiratory tract, and some of them can translocate into other organs, get into the bloodstream. So from a health perspective, they're very important. Now let's look at the same data from the same day at the same time, but on a mass basis. Now that pink line that I showed you is collapsed to the bottom. So on a mass basis, those ultrafine particles that are very important for health don't really represent much in terms of mass, right, in this particular scenario. What you see here is the mass contribution of particles. So while we're cooking the rice, before you saw a bunch of ultrafine or sub 100 nanometer particles, now we don't see them anymore. And then what you really see is increase in particle mass loadings when we added vegetables to the oil and then when we added the sauce. And these particles range broadly in size from 0.5 micrometers, the blue line, all the way up to 20 microns, the biggest, the green line. And that's consistent with previous data that shows that when you're cooking with an open pot with frequent stirring happening all the time, all of that bubbling leads to the formation of larger particles. But there's really a broad range here on a mass basis. So now if we zoom in and only look at PM1, so particles 1 micrometer in size or smaller, we can actually take a look at the data from Professor Peter DiCarlo at Drexel University, who is here today, and look at the data from his aerosol mass spectrometer, and then we can see a chemical fingerprint of those particles. So the AMS spectrum here is showing mostly the green regions, which are similar to oleic acid, or they did some comparisons between that and just splashing the pan with oil, and found that the signal that they're observing on a mass basis is really mostly coming from the oil. You can still correlate them to when the veggies were added to the oil and when the sauce was added, but the fragments detected by the AMS mostly had CH and CHO groups. Now, if we zoom in a little bit more and try to look at just at the bottom of that chart, you can see that there's a little bit more going on. When we add the food, there's actually emissions of organic nitrogen-containing compounds associated to the food. There's also a little bit of chlorine and other things that you can see, and you can tie those because this is a time-resolved measurement. You can time those with the activities that were going on at the time, adding the vegetables, adding the sauce, for example. So that was just a little bit of the kind of information that we're getting from this study, just to give you a flavor. Some of the preliminary results we've observed so far from home chem were, of course, related to high emissions of particulate matter. So I focused on particulate matter today, even though we had also VOC measurements and other things. What we observed was that the use of the propane, in our case it was a propane oven and stove, was the main source for ultrafine particulate matter, less than 100 nanometers in size. The food was the main source for fine particulate matter, unless there's a lot of stirring going on, like in the case of the stir fry, then you can get all the way up to coarse particulate matter. Occupant movements was the main source of coarse particulate matter, because as we're walking, we're resuspending dust from the ground, we're shedding particles and skin cells from our own bodies. We are also observing a lot of interesting chemical reactions that take place during cooking activities. We're still probing into those data, and what a lot of results are showing is that the surfaces around the house throughout that month-long period of activities was evolving and changing as their pollutants were depositing onto them. The final message that I'd like to leave with you today is that we understand our pollution processes much better outdoors than we do indoors. These questions are still pretty open-ended, and even with the wealth of data that we've collected at home chem, what we're finding is it's opening up new questions, answering some, but opening up many others. So it's important to look at the indoor environment. As was mentioned before, we live indoors and we spend a very significant amount of time in our own homes where we are introducing all of these chemical reactions ourselves. So with that, I'd like to acknowledge funding from the Alfred P. Sloan Foundation for this study, our massive team of collaborators, and I'd like to mention our network, indoorchem.org. If you're curious about indoor chemistry, please visit our website. We have descriptions of all the projects that are related to this group, and we also have a pretty healthy Twitter account that shares the latest papers that have been published and blog posts and things like that. So I welcome you all to join the community there. Thank you.
So we have a few minutes for questions. If you want to use the microphone for questions. And I think
Hi, I'm Gina Saganek. I'm the CEO of a nonprofit called the Healthy Building Network, and we do research and education mostly around the toxic chemicals in building products and how they impact. So this has been a phenomenal morning so far, listening to all your research. It's pretty incredible. Before I went to Healthy Building Network, which was about 3 years ago, I spent the first 20 years of my career developing affordable housing for marginalized communities. So I'm a warrior for health equity and trying to really figure out how all of this applies. So I'm not a chemist. I always say I'm more of a chief translator of the amazing chemists, and how does this information translate? So, and how can it be applied? So what I'm really curious to hear from you all and the rest of the presenters today is, are you doing any research in how people who are living in areas where there are factories and the air is more polluted than maybe some of the research homes, and where they're living in often communities with more dilapidated housing, they're in multifamily housing where you not only have impacts from who's ever coming in with deodorant, but all your neighbors who have deodorant. And people who are working in the factory all day and bringing home pollutants and just their exposure. So I know you all know very well that the marginalized communities, people of color, low-income populations, kids are much more exposed. So I'm super curious to hear how some of your research is maybe looking at that side of the equation and what we can do in those communities to make sure that those groups aren't facing the health consequences, who often don't have health insurance on top of that. So I appreciate that. Thank you.
Go for it.
Yeah. Okay. Is this on? Yes. Well, thank you so much for bringing that up. Those are incredibly important topics, especially if you think about the U.S. building stock. You know, there are so many different types of homes, and I know there are a lot of, I haven't done any of that research myself, but I know there is a body of knowledge on linking the leakiness of homes with their age and whether or not energy retrofits have been applied, especially in low-income housing. There's a lot of research there, but questions still remain on the effectiveness of these energy retrofits in making the house more airtight versus leaky, and that's about your point of outdoor air pollution infiltrating in. There are some studies as well on the effects of building insulation. There are many low-income housing units that have missing spots of building insulation. This reminds me of research from Dr. Getty Mainellis from Rutgers University. He looked at homes, buildings in the state of New York, and they were looking at New York, New Jersey, and they were looking at potential penetration of outdoor air pollutants just through these areas where the insulation is missing. So there's a lot of research on that, but I don't think there's a general consensus. When it comes to indoor sources, the same applies. We can't dictate what people do in their homes, so there's a lot of variability there in terms of indoor sources and behaviors, and I'm sure my colleagues might have something to add.
I want to add one thought. Oh, Barb, go ahead.
Just, I wanted to mention that there was a study called the RIOPA study several years ago, and that it was 150 homes in each of 3 cities, and the homes were over-selected for homes particularly near outdoor sources. And so they did look at the effect of distance to source on VOC exposures and on PM particulate matter, also I'm one of the PIs on that study. And I don't want to tell you what we found because it was long enough ago that I'm not going to get it right. So we can talk about it later today if you'd like.
So
Looking to work with those communities, we have some programs, and if you want to do research in those communities, we have a program called Home Free.
Great. I wanted to say one thing in response to you. Part of what you're seeing today, at least with my talk and Nina's talk, is the result of research that was funded specifically to look at chemical processes, to look at fundamentals in non-problem homes. A lot of the techniques that we're applying can be applied to other places that have problems. I actually think that one of the most interesting things to do next would be large apartment buildings where there's a lot of indoor-outdoor exchange, but there's a lot of breathing what your neighbor is cooking. And there haven't been a lot of studies with the kind of instrumentation that we've been using in that type of environment, but I think they're really critically important. And hopefully one of the things that comes out of this meeting here is some connections with organizations that have other interests. You know, Sloan's interest is in fundamental chemistry processes, but I know a lot of you are coming from a different perspective and want to support different kinds of work. And so that's why we're here to communicate.
Can I add one more point, if you don't mind?
11% of Americans now live within 100 meters of a freeway, a highway, or a really busy roadway. And the body of knowledge of health effects of people that live in close proximity to freeways is overwhelming at this point, wide range of health effects. So I think when you look at that versus people that live near major industrial facilities, there's more health data that suggests that living close to a roadway is as or more important. And so I think that's an area we need more research on.
And there's a lot of affordable housing for communities where the neighborhoods went through, so all of that.
Right.
Always pointing to that. Thank you.
Can you repeat her comment, because we can't hear her? Can you repeat it, please?
Yeah, maybe she can speak to the mic. That's a good reminder for everybody with questions.
Yeah, thank you. I just mentioned that those freeways, that's where a lot of the affordable housing is built because of the NIMBY, not in my backyard, and it's just where poor communities, that's where highways were put through. So again, that goes back to marginalized communities, the highways.
I do want to make an announcement that the people that are watching the webcast can submit questions online in the chat box or on Twitter using
Here's the hashtag, AAAS.
the hashtag on the screen.
So I think the speakers did a very good job of educating me about why total VOCs, just looking at that, is not very useful. So, since I don't consider eating oranges or making toast dangerous activities, has there been progress in, relatively quicker or easier ways of, discerning the dangerous VOCs versus those that are not?
It's a great question. I guess people are looking towards me. And I think that the research that I showed was largely done in sort of a discovery mode, right? And we were trying to understand what's there, how's it behaving. We could use so many different filters to look at that data. One filter could be, what are the chemicals that we have health concerns about? What does the health community worry about? And we are doing that as well. So there's a paper that just came out on the phthalates in the home and how they behave, which are some of the compounds that Rich talked about. But I think that it's absolutely important to look at that particular issue. However, one thing I worry about is that the health community often focuses on chemicals that they already know have health impacts. But what we're trying to do is take a really broad spectrum approach to see what is there. And I think that some of our results are pointing to chemicals that haven't been identified necessarily as having health effects, but may be important. And so we need to not just restrict ourselves to the things that the EPA already knows are a problem, right? So that's my answer.
And also, too, I think there's research, too, to start to look at the actual mechanisms of the human response. And that's really the challenge. Paula mentioned earlier about regulations. Outdoor regulations can focus on specific chemicals, but the indoor receptor is the human, and we don't know everything we need to know yet to decide which chemicals or what classes of chemicals. And I think that, we're in the mixture, and so you've got to think about a lot of synergistic effects. And how oxygenated species and particles kind of react with us. So that's still coming together. So,
and as a plug for Ray, if I may, his group and some of his colleagues at NIOSH are probably one of two groups in the world. When you look at reaction products where we don't have any good tox data, they've been sort of leaders in trying to decipher the health effects of these reaction products, which we haven't focused much on until recently because we're identifying them at this time. So I think if you Google NIOSH and find Ray and his group, there'll be some information there about sort of prioritization of oxygenated compounds.
right, we're trying to figure some of that out.
Hi. So I had a quick question to follow up kind of the first question, and also the talks we saw today primarily focused on residential environments. And I'm looking around this room, and there's probably at least 60 people in here, and we're going to be in here for 6 hours or so. So that's 360 person hour exposure equivalent in 6 hours. And my wife and I, 2 people in a bedroom, where we spend the most of my time in my house, that would be 20 to 25 days of sleeping 8 hours a night, which doesn't happen because we have 2 kids. But, so in terms of priority spaces, is the home, maybe for my personal exposure, the most important, but for an integrated people exposure, do we need to start considering other high occupancy spaces as places to do more of these focused studies as well? The question to you guys.
I'll say the home is very important. You've already seen the numbers in terms of the number of years we spend it, but it's also where children spend most of their time. And, children, infants are pretty important receptors of air pollution, especially if we're talking about things like endocrine disrupting chemicals, et cetera. You're right, though. I mean, we have to study beyond the home. Schools or environments where you have your most concentrated, density of people per square meter, right? And so school environments are another environment that needs to be studied, again, focusing on children. Hospitals, office places, we need to study all of those. I think we all focused on homes because we have data for homes and because homes are where we spend the largest fraction of our lives. Good point, Pete.
Yeah, hi, Bill Bonfluth, Penn State Architectural Engineering. Rich showed some interesting data on effects of temperature and humidity on air quality, and it raises 2 interesting questions for anybody who is involved in design and operation of buildings. First one is, where do you come down on temperature and humidity from the point of view of set points if there's now an impact on air quality, and at the same time it's coupled to the thermal comfort of the space, which actually, if you look at Bill Fisk's research on the cost of poor indoor environmental quality, thermal environment is more costly than air quality, given the way we maintain buildings. So is anybody looking at these interactions and the implications for the cost of running a building based on what science is starting to tell us?
I think Michael Waring at Drexel has recently published a paper, or is in the process of doing that, of showing that linkage.
You mean like between ventilation and economics?
Yes.
I was on the committee of his 2 doctoral students who did that work. So yeah, it's related, but I think we have a ways to go.
So my last slide, which I didn't get to go through, there was, one of the bullets for future work is not only understanding the health impacts and the productivity impacts, but also the economic impacts of indoor chemistry and environmental conditions. How we define environmental conditions with thermostat settings, set points, et cetera, is important, and we really need more research in that area. I think if this field progresses, one of the things that will help it progress is understanding the costs of not doing anything, right? So I think it's an area that needs a lot more research, Bill, and it's a great point.
I have another short one for Alan while I'm here. You sure they weren't just making a lot of toast instead of drinking at that party? But I was interested in the fact that you really didn't see any difference between winter and summer. And you made the comment that the airflow was from the bottom through the top. And if you had a climate where there really was a winter and a summer and you didn't have a pressurized building, you'd expect the stack effect to reverse between winter and summer. Why do you think that was?
It's interesting. The stack effect didn't reverse between winter and summer. And where this building was, it does get to below freezing temperatures in winter, probably 20 nights a year, and it certainly happened during our study. But I only had 14 minutes, although I think I took a few more. There's some more detail that I could have told you.
It's terrible being a moderator.
One of the things I want to say is what I showed is the concentration winter versus summer on a log scale. So there's a lot of room for slight differences, but the main point that I want to make is the emissions in the winter were actually about half of the emissions in the summer. The emissions in the summer were twice as high, but the ventilation rate of the building was twice as high in summer. So we ended up with the same rough average concentrations winter and summer, but it's because both the ventilation and the emission rates changed between winter and summer. So that's maybe a subtlety that's of interest to people who are into the processes But in terms of what people were exposed to, it was similar in winter and summer for the most part.
Thanks, that helps. Appreciate it.
I'll get the last question from a write-in question. Similar to emissions of greenhouse gases dominated by fossil fuel combustion, do you think a similar analysis for indoor VOCs would lead to fossil fuel origin as products of combustion or byproducts as well? Shall I read? I'll read the question again. You want me to read again?
Sure.
Okay. Similar to emissions of greenhouse gases dominated by fossil fuel combustion, do you think a similar analysis for indoor VOCs would lead to fossil fuel origin as products of combustion or byproducts as well?
Well, okay, a couple of comments. At the risk of going first, one source of indoor chemicals, particularly NOx, is burning fossil fuel. It's cooking, right? So there is importance of using fossil fuels indoors, but also a lot of consumer products are made from petroleum, petrochemical, and there was actually a really interesting paper in Science last year by Brian McDonald that focused on consumer product that were made from petrochemicals and how much emissions from those petrochemicals went to the outdoors. In the indoors, I think there are sources like that, but they're not the only sources. There are lots of other sources, and in most cases, I think they're probably not the dominant sources. But they exist, and in certain kinds of indoor environments, you may have a lot of those. But they're from consumer products that people bring into their homes.
Okay, so in the interest of time, we'll close this session. I'd like to thank all the speakers.